So we resume now with this basic functional analysis revision. For this part of the course, the reference book I have in mind is the book by Conway called A Course in Functional Analysis, second edition, Springer 1997, and this should be available in the library. Okay, so we start with really the basic definition of functional spaces that we will be using throughout the course, and let's start with the one of the most basic ones, which are the metric spaces. So given a set X, and I want to stress the fact that X is just a set with no other structure on top, so there are no operations defined on X, for example. And given a function d from x times x into the non-negative real numbers, we say that d is a metric over x if these three properties are satisfied. So the first property says that the distance between 2 points is 0 if and only if the points coincide. The second property is the symmetry and says that the distance between 2 points is the same independently on how you compute it. And the third one says that is the triangle inequality. It says that the distance from x to another point y is less or equal than the distance from x to another point plus the distance from such point to y. So as you would expect in as it happens in the Euclidean space. So if D satisfies this property, the pair XD is called a metric space. So let's define two basic notions. The first one is convergence in metric spaces. So for a sequence in X, we say that Xn converges to X0 if this is the definition you expect. For every epsilon greater than 0, you can find some n epsilon such that the distance between xn and x0 is less than epsilon whenever n is larger or equal than n epsilon. And for the definition of Cauchy sequence, you have that a sequence is Cauchy if the distance between 2 points in the sequence is small whenever the indices are large enough, as usual. So let's pass to a very important notion, the one of completeness. A metric space XD is called complete if every Cauchy sequence in X is convergent to some point x0 in X. It's, I don't know, probably you remember this, but the converse is always true. So if you have a convergent sequence, this is always Cauchy, and it's actually very easy to verify. Actually, Cauchy implying convergent is something that you need to require. It's not always true. Okay, so let's see how we can interpret a metric space as a topological space, so that we can use definitions from general topology applied to the metric space that we have at hand. So for a metric space XD, consider this collection of sets tau. So tau is the collection of all sets in X, such that if you take a point in a set A, then there exists a radius epsilon such that the ball of radius epsilon centered at X is fully contained in A, and this has to be true for all the points in A. This is the notation for the balls of radius epsilon in a metric space. So it's just a notion of ball with respect to the distance d. Okay, if you define t in this way, one can see that tau, sorry, if one defines tau in this way, one can see that tau is a topology over X. And as usual, the sets in tau are called open. and a set in X is closed if its complement with respect to X is open. Okay, now let's introduce a couple of common notations. So if X tau is a topological space and A contained in X is a subset, we denote with this symbol, so A with a circle on top, the interior of A, which is defined as follows. So the interior of A is the union of all open sets such that the open sets are contained in A. Okay, and we also denote by A with a bar on top the closure of A, which is defined as the intersection of all the closed sets containing A. So in other words, the interior of A is the largest open set which is contained in A, while the closure of A is the smallest closed set which contains A. So, and now with this we can define these two notions here. So the notion of density, if you're given a metric space X with metric D, we say that a subset D is dense in X if the closure of D is equal to X. So the closure is taken with respect to the topology induced by the metric D. And in a metric space one can actually see that the closure, so this set here, can be characterized as the set of limit points of all the convergent sequences with values in A. Maybe I will leave this as an exercise to verify. So the second notion is the one of separability. We say that a metric space XD is separable if there exists a countable subset D which is dense in X. So a space is separable if it admits a countable dense subset. Okay. Obviously, like for these examples, you can, for an example, you can think of X to be the Euclidean space R, Rd, for example, and obviously Rd is separable. You just take the rational numbers, and that's a countable set which is dense with respect to the Euclidean metric. Okay, another notion that we need is the one of limits. So given two metric spaces with different metrics, dx and dy, and given a set u in X which is open and a function from u to y, we say that f of x converges to some element L of y as x goes to x0. In symbols we denote it like this, as usual, if for every epsilon greater than 0 there exists a delta such that the distance of f from L is smaller than epsilon whenever the distance of x from x0 is smaller than delta. Okay, and with this you can immediately define what's continuity in metric spaces. So given two metric spaces, u in X open and f a function from u into y, we say that f is continuous at a point x0 in u if f of x converges to f of x0 as x converges to x0. And obviously f is continuous in u if it is continuous for each x0 in u. Okay, so now we see a second class of spaces which are called the NOR spaces, and this is a class which is less general than metric spaces. So what we actually have in the end is that every norm space is a metric space. So given a vector space over R, so this is the first difference. Of course, here we are assuming that we have some structure on X, specifically a vector space structure, meaning that there are we have two operations, which are the sum of two vectors and multiplication with a scalar in R. So giving a real vector space X and this function here from X into the non-negative real numbers, we say that this function is a norm over X if these properties hold. So the first property says that the norm of the norm of X is 0 if and only if X is equal to 0. The second property is called one homogeneity, and it says that if you multiply X by a scalar in the field R and you take the norm of this new vector, this is the same as multiplying the norm of X by the absolute value of the scalar lambda. And the third property is the subadditivity, meaning that if you take the distance, if you take the norm of the sum of two vectors, then this is less or equal than the sum of the two norms. And so if X with such a function satisfies these properties, then this pair is called normed space. So as I was mentioning before, if you have a norm space X, you can define a distance on it in the following way. So the distance between 2 points is just the norm of the distance, and this defines a metric over X. In particular, from the remark on the topology we saw before, we have that the norm space X is also a topological space with the topology tau induced by the metric D, which in turn is defined in this way. And by convention, like in the following, we all the topological notions that are given on norm spaces are given with respect to the topology tau induced by the metric. Okay, so this is another less general class of spaces, the Banach spaces. So given a norm space, we say that it is Banach if the induced metric space is complete. So that's the definition. So a Banach space is a complete normed space. Okay, now that we have this vector space structure, we're able to define linear operators between norm spaces. So given xy to norm spaces and a function from x into y, we say that t is linear if this property holds. So I mean, basically, if you apply t to the sum of two vectors, the result is t applied to the first vector plus t applied to the second vector, and the second requirement is that t applied to lambda of x is equal to lambda t of x, and these two properties are summarized in one line like this. And the second definition is that an operator t is called bounded if the supremum over the unit ball of x, so all the vectors in x with norm less or equal than 1, of the unit ball of t, the image through t, so the norm of tx with respect to y is less than infinity. So basically this says that if you take the unit ball b in x, then t of b has to be bounded in norm, in y norm. So this is something that I'm sure you know already, but just as a reminder, if you have a linear operator between norm spaces, then t is continuous if and only if t is bounded. And this is true for linear operators. And here continuity obviously is intended with respect to the norms on these two spaces. Okay, can now define the space of linear continuous operators. So given two norm spaces x and y, we define with this capital L the space of linear bounded operators between x and y. And in the particular case where y is equal to the real numbers, this space here is called x star, which is usually called the dual space of x. So just to stress the fact that here the dual is taken with respect to the norm on x. So you're actually requiring the operators from x into r are continuous with respect to the norm of x and the Euclidean distance over r, of course. So a remark is this one is pretty straightforward. So if you consider this space of linear boundary operators, this is itself a vector space over R with the operations defined as you would expect. So these T1 and T2 are operators. And the second observation is that Lxy is also a norm space with the norm given by this relation. So you remember that if T is bounded, a bounded operator satisfies that this quantity is less than plus infinity. So what we actually require is what we actually call the norm of T is just this actual quantity here. The third observation is that if y is Banach, then the linear operators between x and y is itself a Banach space. And I want to stress out that this is regardless of whether x is Banach or not. So x could be just a norm space, and if y is Banach, then the linear operators from x to y are Banach as well. And as a straightforward corollary of 3, we have that if x is a norm space, then x star is Banach, because R is complete. Okay, now that we have all this technology of dual spaces, we can define a few convergences. So let's see, given a norm space X and sequence in X and a sequence in the dual, we say that Xn converges strongly to X0 if the distance, the norm of the difference between Xn and X0 goes to 0, as n goes to plus infinity. Then we say that Xn converges weakly to X0 if this is true. So this means that whenever you evaluate a function in the dual on Xn, you should obtain phi of X0 in the limit. And this has to be true for all the functions in the dual. Then for a sequence of functionals, we say that phi of n converges weakly star to phi 0 if the functionals converge pointwise. So whenever you evaluate the function at some fixed point x, this has to converge to phi 0 evaluated at the same point, and this has to be true for all the points in x. And finally, as x star is a norm space, as we discussed here, so in particular here you can take as y the real numbers, and you get the dual is a norm space with this norm here. So as it is a norm space, we also have a notion of convergence there with respect to the norm, and so we just say that a sequence of functional converges strongly to some point f phi if the distance with respect to the dual norm goes to 0 as n goes to plus infinity. So here first note on weak convergence in relationship with strong convergence. We have that this immediate to check by the very definition of bounded operators. We have that xn converges strongly to x0 implies that xn converges weakly to x0. So strong convergence implies weak convergence. The reverse implication is not true in infinite dimensions. It is true in finite dimension. So in finite dimension, basically weak convergence and strong convergence are the same, but that's not true in infinite dimensions. And a counterexample is, for example, this standard counterexample here. So take as x the little small l p space. So this space denotes the space of sequences of real numbers, such that the p norm, so if you take the series of the absolute values of these real numbers to the power of p, then you should get something which is finite. And here p is between 1 and plus infinity excluded. So with this norm, so obviously this defines a function on the space X, and we have that actually this defines a norm over LP. Okay, so LP is a norm space. It's actually Banach space. So the counterexample is as follows. Just take the sequence which has all zeros except 1 at the jth position. Then you can check that E of j converges weakly to 0, but as you can see, the norm of E of j is constantly equal to 1, and obviously this does not converge to 0, showing that weak convergence does not imply strong convergence in general. Okay, so now that we have all these notions of convergence, we can define the notion of compactness, which will be very important throughout the course. And so the definition is as follows. Suppose you have a norm space X and a subset K of X and a subset K tilde of the dual of X, so X star. We say that K is compact if for every sequence in K you can find a point x0 in K and a subsequence of xn such that x and k converges to x0 as k goes to plus infinity. I want to stress the fact that it's very important that the limit point has to be in K, okay, for K to be compact. Second definition is compactness with respect to the weak topology. So we say that K is sequentially weakly compact if for every sequence in K you can find a limit point in K and a subsequence such that x and k converges weakly to x0 as k goes to plus infinity. And similarly we can define sequential weak star compactness in the dual. So K tilde, which is a subset of the dual, is said to be sequentially weakly star compact if for every sequence of functionals in here I should have said K, so let's correct this. So for every sequence of functionals in K tilde, you can find another functional phi 0 in K tilde, such that along a subsequence phi of nk weakly star converges to phi 0. Okay, so with this definition comes a big warning between the difference for the difference between sequential compactness and compactness with respect to some topology. So remember that if x tau is a topological space, then a subset K is said to be compact if any open cover of K admits a finite subcover. So this means an open cover of K is a collection of sets AI such that the union of these AIs contains K. And this open cover is arbitrarily large. So basically the set of indices could be uncountable or could be whatever. But no matter what happens, if K is compact, you can always find a subset of these indices which is finite, and such that the new union of the sets with indices in this subset still cover K. Okay, so this is the classical topological definition, which seems to be different from the sequential definition, which is given a sequence in the set K, you have to find the limit point which is still in K for some subsequence. And actually what happens is that if the topology tau is metrizable, meaning that tau, so metrizable means that tau can be written as tau d where d is some distance on x, where tau d is defined as we did before. So okay, let's find it. It's quite behind. Okay, I can't seem to find it. There you go. So given a metric space, this this topology is what we call tau d, the topology induced by the metric. So basically, a space is topology is metrizable if you can find a metric such that the open sets can be characterized in terms of the distance. Okay, let's go back to the previous point. Okay, so the what I was saying is that if a topology tau is metrizable, then sequential compactness is equivalent to compactness. So the definition with the open covers is the same as the definition with sequences. And what happens is that, so for on a norm space, obviously with respect to the norm, you get a metric space, and so x tau with the topology induced by the distance is metrizable. So in that space, the compactness and sequential compactness are the same. So with respect to the norm, they're the same notions. However, for the weak topology on X and the weak star topology on X star, these notions are not the same, because the topologies weak star and weak topologies are in general not metrizable. However, if we add some assumptions on X, we can actually relate compactness to sequential compactness, and this happens in these two interesting cases. So the first case is if X is a Banach space, then sequential compactness and compactness are the same thing, and this is actually the Eberlin-Mullian theorem that you can find in the book of Conway. I was recommending at the beginning of this second part. And the second interesting fact is that if X is a separable Banach space, then sequential compactness and compactness are equivalent for the for the weak topology, for the weak star topology. Sorry. So actually here there is another typo that I'm noticing. So here is weak sequential compactness and weak compactness, and here we have weak star sequential compactness and weak star compactness. Sorry, as you noticed during the video cut, I actually changed this paragraph, but you can find it anyways in the uploaded lecture notes on Moodle. So now that we talked about this warning about compactness and sequential compactness, we pass to state one of the main theorems about compactness with respect to weak topologies in infinite dimensional spaces, because I mean, as you know, as you probably know, strong like for example in RD, so in the Euclidean space, you know that set is compact if and only if it is closed and bounded. But in infinite dimension, if you take for example the unit ball with respect to the norm, which is bounded, this is not necessarily compact, although it is closed. So this is one of the big differences between finite and infinite dimensions. So, and the Banach-Alaoglu theorem gives sufficient conditions for for the unit ball to be compact in weak topologies. So take a norm space X and denote by B the unit ball in the dual of X. So all the functions in the dual such that the dual norm of such functions is less or equal than 1. Okay, then we have that B is always weakly star compact. So this is always true if X is a norm space. So notice that here I'm saying weakly star compact and not sequentially weakly star compact. Point 2, if in addition X is Banach and separable, then the unit ball is actually also sequentially weakly star compact. So with these two additional assumptions of being Banach and of being separable, you also get that the unit ball is also sequentially weakly star compact and not only weakly star compact. So here I'm stressing the fact that we have to talk about sequences or sometimes, or we have to talk about just compactness with respect to the topology sometimes. But actually in all the practical examples that we will see throughout the course, all the spaces will always be separable and Banach. So we're actually always in the situation of point 2. Okay, so there is a corollary of this Banach-Alaoglu theorem, which concerns the weak compactness of the unit ball in X and not in the dual. And for that corollary, we need the definition of reflexivity. So let's see how we define reflexivity. Given a norm space X, consider the dual X star. So remember that now X star is still a Banach space because X is normed. So in particular, there is a norm on X star, and we can consider again the dual, which we call the bidual of X. So the dual of X star, which is denoted by X star star, is just the dual of X star with respect to the operator norm. So this is important, that you are considering functionals from X star, you're considering functions from X star into R, which are continuous with respect to the operator norm, okay, on X star, and obviously the Euclidean norm on R. So these will be the elements of the bidual of X. Oops. Okay, so once the bidual is defined, we can consider the canonical embedding, which is a map J from X into the bidual, which is defined as follows. So take a point X, small x in capital X, and this has to define an element in X star star, meaning a function on X star. So taking phi an element of the dual, we define Jx of phi as just phi applied to X. And this clearly defines a function in X star star star. You can actually check that this is linear continuous with respect to the strong topology on the dual. So what we have for this canonical embedding is that J is actually an isometry, meaning that the norm of the bidual element defined by J. So again, this is the norm, the dual norm in the bidual. So this norm here is equal to the norm of the starting point X in the starting space X. Okay, with this machinery of the canonical embedding, we say that X is a reflexive space if J is surjective. So this means that all the elements of the bidual can be written as the image through J of some point in X. And actually this is a bijection, okay? And is also an isometry because of this relation here. Okay, now that we know what reflexivity means, we can state this corollary of Banach-Alaoglu. So, given a norm space X, consider the unit ball in X. Again, here there is another typo. So, all the elements in X which have norm less or equal than 1. Then, fact 1, we have that if X is reflexive, then B is weakly compact. Again, this is just weakly compact and not sequentially weakly compact. And if in addition to be reflexive, X is also Banach, then B is weakly sequentially compact. And as I was mentioning before in the situation for the Banach-Alaoglu theorem, here we have that basically we will always be in the situation of point 2 when in the applications. So whenever we have a reflexive space, more often than not, this space will be Banach. So actually the unit ball will be weakly sequentially compact rather than just be weakly compact. Okay. So as a consequence of the principle of uniform boundedness that I'm not stating here, and because I don't think we will ever need it explicitly throughout the course, but you can find it in the book of Conway if you are curious to see the statement. And maybe you will have to find it because probably I will put some exercises on weak convergences that we require to apply this principle. So by exercise you can go and find it basically and apply it in some very simple situations. So as a consequence of this principle, which we will abbreviate like this, if you have a Banach space X, then point 1, taking a sequence in X such that the sequence converges weakly to X0, we have that the sequence is bounded uniformly in norm. So if you take the supremum over n of all the norms, you get a finite number. This translates into saying that weakly convergent sequences are bounded. Okay. And point 2, we have the analog statement for the weak star topology. So weakly star convergent sequences are norm bounded in the dual. Okay, as you can see, these two are kind of the converse of, if you want, of the Banach-Alaoglu theorem and the corollary, because as we saw, if you have a bounded sequence in the Banach-Alaoglu theorem, we are saying that the unit ball is weak star compact or weakly compact. Now the unit ball is bounded, and by scaling it you can take any bounded set basically. And you know by these two theorems that if you take a sequence in this in a bounded set, then the sequence has a convergent subsequence with respect to the weak or weak star topology. And these two are kind of the converse statement. So if you have something that converges weakly, then it must be bounded uniformly. Okay, another important notion that we will need throughout the course is the one of lower semi-continuity. Okay, so given a metric space X and a function defined on X, we say that F is lower semi-continuous at a point x0 in X if for every sequence in X such that xn converges to some point x0, then the value of F at x0 has to be less or equal than the liminf of F of xn. Okay. So this means that the smallest accumulation point of this sequence here, fxn, has to be larger or equal than f of x0. Okay, so just to put things in perspective, I mean, remember that you always have this inequality, no, not this one, lim sup for n that goes to plus infinity. So this is from basic analysis. These are just real numbers, fxn and fxn. So the liminf is always less or equal than the lim sup. And if you actually prove that this is true, then you're just saying that that f of xn converges to f of x0. Okay, so you're just saying that the function is continuous. So being lower semi-continuous means that only let's change color. Being lower semi-continuous means that only this relationship here holds, and being upper semi-continuous means that only this relationship holds for all convergent sequences. And obviously if both of these hold, then your function is continuous. Okay, let me remove these nodes. Okay, this was strong continuity, strong lower semi-continuity, sorry, with respect to the metric. In norm spaces we also have the weak topologies, so we can talk about weakly lower semi-continuous and weakly star lower semi-continuous. So given a norm space X and a function f defined on X and another function g defined on the dual, we say that, as you can imagine, f is sequentially weakly lower semi-continuous at x0 if this relationship holds for all the sequences in X such that they converge weakly to x0. Okay, so you have to check this relationship for this condition for all the convergent subsequences, weakly convergent subsequences. Weakly convergent sequences. And analogously, you can say that G is sequentially weakly star lower semi-continuous at some point phi 0 in X star if the value of G at phi 0 is less or equal than the lim-inf of G of phi n, where phi n is any sequence in X star which converges weakly star to phi 0. And again, this has to be checked for all the sequences weakly star converging to phi 0. Okay. And again, like with compactness here, I'm stressing sequentially because actually you can talk about weak lower semi-continuity and weak star lower semi-continuity just in terms of topologies like you do with continuity. But again, we will never need this in practice, so I'm not even making a difference between sequential and non-sequential lower semi-continuity for weak topologies. Okay, so these are two examples of semi-continuous functions. Given a norm space X, point 1 says that the norm in X is weakly sequentially lower semi-continuous. So whenever you take a sequence converging weakly, then this inequality holds. And the second one is that the dual norm is weakly star sequentially lower semi-continuous. So whenever you take a weakly star converging sequence, then this relationship holds. Okay, and this will be important in direct method arguments. So, spoiler alert, I was going to talk about Hilbert spaces, and I realized that we're probably anyways approaching the end of the session, so I don't want to start this new topic and having to stop midway. So I will just leave it for next time. And anyways, something else. So while I was editing these videos, I realized that since I'm explaining something that I had already written offline, so it's just like I'm talking on some slides, probably I am going too fast. At least this is what I think. So please send me an email if you think I am going too fast. Okay, so next week we are going to resume with this functional analysis revision, and the last topic of this revision is Hilbert spaces. And then we're going to move on to something that will be hopefully new for you, which is calculus in Banach spaces, so Fresnel derivatives, Gateau derivatives, and so on. Also in the exercise course, I think that next week you will have you will have to do the first set of exercises, and this will be just 4 very easy exercises on the topics discussed in this revision. So they're just for, I don't know, remembering things in case you forgot from your functional analysis course. And okay then, see you next week.